Warm greetings to one and all. I am Hasini Kethavathu, roll number 1043. As a part of the CS1116H video assignment, I am going to talk about the IEEE 754 floating point representation. So this is the set 1 question 1. In order to be able to solve this, we need to know about the IEEE 754 representation. Let me introduce the system. It is an international standard for representing floating point numbers. It was published by the Institute of Electrical and Electronics Engineers in 1985, revised later in 2008 and 2019. It ensures consistency in the method of representing floating point numbers across hardware and software. It is used widely in CPUs, GPUs, and compilers. Let us dive into the basics of floating point numbers. So the universe of integers is discrete, but that is not the case with floating point numbers. Between two floating point numbers, there exist infinitely many floating point numbers, and these can have very large or very small values. In order to represent these floating point numbers, our base is 2 in IEEE 754 representation. And of course, the system is very necessary to handle scientific values and to represent the values of irrationals like pi. There are two standard forms of IEEE 754. The first one is single precision format, in which 1 bit is dedicated for sign, 8 bits for the biased exponent, and 23 bits for the fractional part. And the double precision, where 1 bit is for the sign, 11 bits are for the exponent, and 52 bits are for the fractional part. It's always a trade-off between memory usage and precision. When we use 64 bits, it takes up more memory, but the number is represented more precisely. Let me explain the 23-bit format. The 1 bit is for the sign. 8 bits is for the representation of the biased exponent in the binary form. And 23 bits is for the representation of the mantissa or the fractional part. The sign bit is 0 for positive numbers, 1 for negative numbers. The exponential part stores the biased exponent, and the fractional part stores the mantissa is for the fractional part. But let's dive into bias and exponent representation. So instead of dedicating a specific bit for storing the sign of the exponent, we add a bias. So the biased exponent is actually the actual exponent plus the bias, which is 127 in IEEE system. And exponent allows us to easily compare the floating point numbers. The scientific notation of numbers is going to be -1 power sign into 1 plus f into 2 power exponent. Here f is the mantissa, as we saw earlier. 1 plus f is called the significant. The exponent is expressed in 2 powers in 2's complement in its binary form, and it's the biased exponent. Numbers lead with 1. This is implicit. And the range of the exponent is going to be 1 to 254 in the binary format, which is -126 to 127 in the decimal format. Last but not the least, let's get to know about some special values and overflow cases in IEEE 754 format. There are two avatars of 0. They differ in the sign bits. For representing infinity, we have positive overflow case, wherein if a positive number has exponent as 128, then it's going to be positive overflow. And if a negative number has an exponent of 128, it's going to be negative overflow. This is the smallest possible negative number. And then we have the case of not a number NaN, which is the result of undefined operations like 0 by 0. And then we have denormalized number cases where we have positive underflow, wherein a positive number has an exponent of -127. This is the smallest possible positive number. And negative underflow, wherein a negative number has an exponent of -127. This is the largest possible negative numbers. Thank you. I now hand over the presentation to...
Hello everyone, I am Anjali Prasad, roll number 1012 CSE branch. Now I will be continuing where Hasini left at. I am doing set 1 question number 1, and my first objective was to convert -12.375, which was given as temperature in the question, to IEEE 754 single precision format that contains 32 bits. So I'll write -12.375 as -1 raised to the power 1 times the closest power of 2, which is less than 12, that's 8. So after 8, we are left with 4. So 12 can be written as 8 plus 4, because since we need to represent it in binary, we need to write it in integral powers of 2. Then we need to represent 0.375 as integral powers of 2, where the powers will be negative. So 375 can be written as 0.25 plus 0.125. This can further be written as 1 times 2 power 3, which is 8, plus 1 times 2 power 2, which is 4, plus 0 times 2 power 1 and 0 times 2 power 0, the sum of which is 0. Then we can write 0 times 2 power -1, plus 1 times 2 power minus 2 plus 1 times 2 power minus 3. Wherever we are adding the powers of 2, for example, we are adding 2 raised to the power 2, we'll multiply it by 1. And whichever power of 2 we are not adding, those numbers have been multiplied by 0. For example, 2 raised to the power minus 1, which is 0.5, we are multiplying it by 0 because we are not adding it. And this can further be written as minus 1 raised to the power 1 times 1100 binary point 011, which is in base 2 or binary base. And then further, we can write it as minus 1 raised to the power 1 times 1.10011 base 2 times 2 power 3 to bring it in the scientific notation. Now, to convert into IEEE single precision format, we know that the MSB, which is the first bit, that is for representing the sign of the number. And since our number is negative, the first bit is going to be 1. Now we are going to write the biased exponent. The actual exponent, as we saw earlier, 2 power 3. So our actual exponent is 3. So our biased exponent will be actual exponent plus 127, which is 130, and its binary representation can be given as 2 power 7 plus 2 power 1, which is as given. So the exponent bits are 1, 0, 0, 0, 0, 0, and 1, 0. Now we are going to represent the mantissa. The significand of the given number, which was the number which was written as base 2, was 1.10011, which can be written as 1 plus f, where f is our mantissa. And thus the mantissa bits will be 10011, anything that comes after the binary point. So the 23 bits of the mantissa are written as follows on the screen. And then we will bring them all together to give our IEEE single precision format of the given number representation. Now we will group them in groups of 4, starting from the rightmost. So the groups of 4 are as follows. We'll start from the leftmost. That the first group is 1100. Its decimal is 12, and 12 in hexadecimal is C. Then the next is 0001, which is 1, and its hexadecimal is also 1. 0100 in decimal is 4, and in hexadecimal as well it is 4. Then 0110, which is 6 in decimal as well as in hexadecimal. And the rest of the bits are 0. So the hexadecimal of minus 12.375 in IEEE single 754 single precision format is 0x C1460000. Here we write 0x to represent that the number has been written in hexadecimal format. Now, in the second part of the question, we needed to convert 22 by 7, which was given as the voltage ratio, to again IEEE 754 single precision format. We will write 22 by 7 as 3 plus 1 over 7. And then 1 over 7 can be written as the sum of 1 by 8 plus 1 by 8 square, which is 1 by 64, plus 1 by 8 cube, and it goes till infinity. So we will write it as minus 1 raised to the power 0, since the number is positive, times 3 can be written as 2 raised to the power 1 plus 2 raised to the power 0, which is 2 plus 1, plus 0.125, which is 1 by 8, plus 0.15625, which is 1 by 64, and it goes on. Then we can, the binary representation will be minus 1 raised to the power 0 times 11.001001 repeating, base 2. Then we will convert it in the scientific notation, and it is written as minus 1 power 0 times 1.100100 repeating, base of 2 times 2 raised to the power 1. And since our number is positive this time, our first bit, the MSB, will be 0 to represent it is positive. Now to represent the actual exponent is 1. So our biased exponent in this case is going to be 128, which is 2 raised to the power 7. So the binary representation for that is given as follows: 1000000. To represent the mantissa bits are, when we write the significand as 1 plus f, the f represents the mantissa bits, and they are as given below. And as the 24th bit is 0, there is no rounding is needed, and the number will be as follows. So we combine everything, and then we again group them in groups of 4, starting from rightmost, and then we write the hexadecimal. The leftmost four bits, they represent 4 in decimal as well as in hexadecimal. Then we have 0, then we have 4, then again we have 9, which is 2 raised to the power 3 plus 1. Then we have 2, 4, 9, 2, and that is the hexadecimal representation of 22 by 7. Thank you. Now handing over to Alishaba.
Hello everyone, I am Alishaba, roll number 1016
7, and I'm going to be doing the second part of my second question, which is instruction encoding. So this was the question that was given. You can see the question is bulky, so we're not going to be using this one. Instead, we've gone through it, and we're going to be given data on this question. So first of all, we're going to start with a 24-bit instruction. So it's given that we have a 24-bit instruction. And we were given that there are 64 registers, which implies that there's going to be a 6-bit address. Then there are 4 addressing modes, each with 2-bit encoding. Now we have the 4 instructions with the 3 types of instructions that's been given. We have 2 registers, a standard instruction which contains 2 registers, 1 addressing mode field, and a 4-bit displacement field. Then we have an extended instruction with 1 addressing mode field and an 8-bit intermediate field. Then we have instructions with 3 registers and 1 addressing mode. Now we are given that there are 32 standard instructions and 16 extended instructions. Moving on, now we have memory instructions. Now we're going to start with the memory instructions to see how we're going to be encoding these memory instructions. So as we can see, we have the different bit encodings. First, I've started with implying that 0 is the indicator bit. So every time an instruction starts with a 0, we are going to know it's a memory instruction. Now, due to the fact that we have 32 instructions, we're going to use a 5-bit opcode. Now, apart from that, we add a 6-bit register 1 address, 6-bit register 2 address, 2-bit addressing mode, and a 4-bit displacement field. All the bits add up to 24-bit address. So we have used every single bit while still indicating exactly what we needed to do. Next, we're going to move on to extended instructions. Now, extended instructions, we have 4-bit opcode because we have 16 instructions. We're going to use a 4-bit. Then we have a 6-bit register 1 address, a 2-bit addressing mode field, and a 4-bit displacement field. Adding all of them, we have 20 bits. Now we have 4 bits remaining. So in this 4-bit, we're going to assign a particular indicator that's going to tell us that it's an extended instruction. So we're going to, I have assumed that the extended instruction starts with 1 and 0. Because if I started with 0, that would mean that it's a memory instruction and we can't do it. So we're going to start with 1 and 0 to indicate the instruction. Moving on, we get to special instructions. Now, special instructions have the format 1 and then 3 X's because we have a 4-bit opcode which includes the indicator. Now we have a 6-bit register 1 address, 6-bit register 2 address, and 6-bit register 3 address, and a 2-bit addressing mode. Adding all of this, we get 20-bit address. Now we have 4 bits remaining. Now this 4-bit needs to contain both the opcode as well as the indicator. So we're going to start the bit with 1, but we're going to exclude the 000 in the X because we are not allowed to use 1 and 000 because we've already used it as an indicator for the extended instructions. Moving on, when we get a 4-bit instruction, we have 3 combinations of X, X, and X. Now we can use this to generate unique opcodes without them all being simultaneously 0 because again, as I said, we have used a particular indicator for memory instructions. We can't have that in a special instruction. So excluding that, we only have, because X can have 2 possibilities, we have 8 instructions. And because we cannot use 1 and 0, we're going to have special instructions at possible maximum. So this was my presentation. Thank you everyone for listening to what I had to say. Thank you.